Hello everyone, welcome to the pre-lab lecture on the green enantioselective aldol reaction. Okay, so the video that you're going to watch this week involves a L-proline catalyzed aldol addition reaction between acetone and isobutyraldehyde. So here's the reaction. We have acetone, we have isobutyraldehyde, and the product of the aldol addition reaction is a beta hydroxy ketone in this particular case. If you're familiar with the aldol reaction, typically it is acid or base catalyzed, but in this case, instead of using a strong acid or base to catalyze the reaction, they're using L-proline, which is an amino acid that's chiral. And this reaction represents a successful mixed aldol reaction. And it's mixed because we're using two different reactants. So it's common for the aldol reaction to use a single reactant with a catalytic base, for example, to convert part of the reactant to an enolate, and then the enolate would attack another of the same reactant. So when you're using two different reactants, one in which will act as the electrophile and the other gets converted to an enolate and acts as the nucleophile, and you achieve a good yield of the product, we call that a mixed aldol reaction. And it's called an addition reaction when the product has a hydroxy group at the beta carbon. If you see a double bond between the alpha and beta carbons, that's called the condensation product. And in this particular video, we're going to be isolating the addition product and not the condensation product. This particular mixed aldol reaction is called the Claisen-Schmidt modification, and I'm going to define what that means for you in a couple of slides. And again, it uses organocatalysis because we're using a small organic molecule to catalyze the reaction instead of a strong acid or base. Okay, let's talk a little bit about the classic aldol reaction. Classically, if you're not doing a mixed aldol reaction, you have a single substrate, and it's commonly an aldehyde because when you use an aldehyde, you get a higher yield of product compared to when you start with a ketone. So if you treat, for example, a simple aldehyde like butanol with sodium hydroxide, part of the aldehyde will then get converted to the enolate. The enolate then acts as a nucleophile and attacks remaining aldehyde, which acts as an electrophile to then produce the beta hydroxy aldehyde product. If you were to take this product on to lose water, that would be form the condensation product, and you would end up with a double bond between the alpha and beta carbon. Let's look at the mechanism of a simple base catalyzed aldol addition reaction. For example, if you take an aldehyde such as ethanol, treat it with sodium hydroxide, you'll get a proton transfer to form the enolate of the ethanol. The enolate then is nucleophilic and it can attack some ethanol that's still in solution, and that's because 100% of the ethanol does not get converted to the enolate. Only about 50% gets converted to the enolate because of the pKa difference being roughly the same pKa for the acid and the conjugate acid. So you still have plenty of ethanol that has not been converted to enolate in solution, and a reaction between the enolate and the carbonyl component, or the electrophile, can ensue where we do a nucleophilic attack on the carbonyl carbon. In order to avoid exceeding the octet on this carbon, we'll show a resonance arrow moving electrons up to that oxygen. At this point, we've formed a new carbon-carbon bond, and that's one of the reasons why the aldol reaction is such an important reaction in organic chemistry, because we're able to form this new carbon-carbon bond. At this point, the alkoxide just needs to get protonated. The best acid we have in solution is water, when we're under base catalyzed conditions. So water will protonate the alkoxide to make an alcohol, which is a neutral and isolatable product. Let's talk about the Claisen-Schmidt modification. It actually takes advantage of the knowledge that ketones are not as electrophilic as aldehydes. So that means that they're less reactive towards nucleophilic addition, where the nucleophile is an enolate attacking a ketone versus an aldehyde, right? Because ketones are less electrophilic, they're going to be less reactive towards nucleophilic addition. The enolate then formed from a ketone can be used to react with an aldehyde because aldehydes are more electrophilic. And this modification is called the Claisen-Schmidt reaction. So for example, if you take acetone, treat it with a base, you form the enolate of acetone. That can be used to preferentially react with an aldehyde as the electrophilic component compared to the original ketone. The reason for this is because aldehydes are more electrophilic than ketones. So this is a successful mixed aldol reaction because they're utilizing an electrophile that's more reactive than the original carbonyl that formed the enolate. So then the enolate formed from the ketone, in this case acetone, would preferentially do a nucleophilic attack on the aldehyde, in this case benzaldehyde, and after protonation with water, we would achieve the beta-hydroxy-keto product. In this particular case, notice the aromatic ring. When there's an aromatic ring here, and the product of the aldol addition reaction still contains an acidic alpha hydrogen, we can continue this reaction further to lose water, get the condensation product, which achieves a double bond between the alpha and beta carbon. And the reason why this forms is this product is very stable because we have increased the conjugation of the entire pi system. Remember, there's the p orbitals all the way around in an aromatic ring. Now those are going to be conjugated with p orbitals on the alpha and beta carbon, as well as the carbonyl carbon and all the way up to the oxygen. So we've extended quite a bit the total conjugated system in this molecule, which is really a stable situation. So when there's an aromatic ring here, it's very easy and it's hard to control the reaction to stop at the aldol addition product. It often spontaneously loses water to get the condensation product. That's not going to happen in the video that you're going to watch because the alkyl group here is an isopropyl group, not an aromatic ring. Okay, let's talk a little bit more about the organocatalysis that's being utilized in the video. So one thing to note is that when you use a secondary amine and you react it with a ketone, those will react together to form an enamine. So if you use a chiral secondary amine, and the most common of that is L-proline, because it's naturally available amino acid, so it's very inexpensive. So if you were to make this secondary amine chiral, right, then you can use the chirality in the catalyst to affect the enantioselectivity in the reaction, right? And so we can use this secondary amine and its chirality to induce enantioselectivity. And in addition to the ability to do that, we also eliminate the need for a strong acid or base in the reaction because the enamine itself will take the place of the reactive intermediate, for example, an enolate. Okay, so let's look at the resonance contributors of an enamine and compare it to an enol and an enolate. If we look at the resonance contributors of the enamine, we have a second contributor where there's a lone pair and a negative charge at the alpha carbon. This makes the alpha carbon nucleophilic and electron rich, very similar to an enolate or an enol. But when you compare the resonance contributors of the enol and the enolate to the enamine structure and reactivity is more similar to that of an enol than an enolate. And the reason for that is look at this positive charge, very similar to the positive charge that's formed with the resonance of an enamine. So the enolate is simply more reactive because the resonance contributors overall have a negative charge, whereas we do have one neutral contributor with an enol and an enamine. Because these are neutral, they're going to more significantly contribute to the overall hybrid. This will be the less significant contributor by far to the overall hybrid. And overall, the alpha carbon is a little less nucleophilic than with an enolate. But regardless, you can see the similarities between all of the structures here, right? Where an enamine essentially is the nucleophilic component, right? That would replace the need to form an enol or an enolate. Okay, as I was talking about before, this reaction actually produces a chiral product. Notice the chiral center here. If we were to not use any sort of chiral catalyst, the product would be produced in a racemic mixture, which means a 50-50 mixture of the two enantiomers possible. Luckily, we are going to be using a chiral catalyst, so we can hopefully expect some enantioselectivity in the reaction. Recall that enantioselectivity means that the reaction produces one enantiomer in greater amount than the other enantiomer. Essentially, there's one major enantiomer and a minor enantiomer. If it was 100% selective for one enantiomer over the other, we would say the reaction is enantiospecific. But if we don't achieve 100% enantiomeric excess and something less than that, then we would say the reaction is simply enantioselective, but not enantiospecific. Okay, let's look at a couple of other reactions that can be achieved enantioselectively using organocatalysis. So recall that the definition of organocatalysis is that we're catalyzing a reaction with a small organic molecule. And the reason why this is unique is because oftentimes catalysts are strong acids or bases. They're not organic, and or they also could be metal catalysts, which again are inorganic. So when we use organic catalysts, it's actually very unique because most catalysts are not organic. Okay, so let's look at this example. This is a triketone compound, and there is a cyclization reaction going on. Notice that we are getting 93% enantiomeric excess, right, of this enantiomer over the other minor enantiomer, and that the chirality is induced by the L-proline chiral catalysts. The solvent in this case is dimethyl formamide, which is a type of organic solvent. Let's look at the proposed reason for the enantioselectivity in this reaction. The first thing is to understand a little bit about how the reaction is proceeding. This is a secondary amine, and as we know, secondary amines can react with ketones or aldehydes to form enamines. In this case, the secondary amine reacts with the carbonyl outside of the ring to form an enamine, which you can see drawn over here. The nitrogen-containing ring also contains a chiral center right on an adjacent carbon with a carboxylic acid group. And this group, of course, with the wedge is coming out at you. Imagine this is the enamine, and here's the link to the other ring in the reactant. Imagine that this ring, right, which contains a dione, could sort of come out of the plane of the paper and in front of the enamine, or it could swing behind, right, and be behind the enamine. And then that would change the facial selectivity of the reaction, meaning that the enamine, which is the nucleophile, would attack the carbonyl carbon of one of the ketones in the ring, either from one face, right, which is the front face or the other face from behind. And that the intramolecular hydrogen bonding from the carboxylic acid to the lone pair on the oxygen of the ketone is essentially placing or coordinating this carbonyl from being primarily in front of the enamine as opposed to swinging behind, where it would not be able to reach with this hydrogen to do intramolecular hydrogen bonding. So the hydrogen bonding is essentially locking this ketone in place, right, in front of the enamine because of this chiral center. As a result, the enamine will attack from one face more than it will attack, right, from the other. And that will lead to the enantioselectivity that we see in the reaction. This is a 3D picture of the molecule that you can see here, right, just drawn in a different way, where we can look at this six-membered ring as sort of similar to a chair conformation, which you might expect for a six-membered ring. So if you notice, when the enamine does its nucleophilic attack on this carbon, we're forming essentially that six-membered ring. Notice that the OH group, which is going to be the carbon with this bonded to this oxygen and then this hydrogen, right, or a hydrogen eventually replaced by the workup, this OH group will end up, right, and axial. And then if you look at the other chiral center that forms right here, the methyl group is also up, right, but equatorial. Okay, so we have the two groups, the methyl and the hydroxyl group up, right, one equatorial, one axial with respect to this six-membered ring. So you can see why they drew them up and up here, right, or why they would form that way. So this is essentially a ring-flipped version of this, where you still see that the hydroxyl group and the methyl group are up and up, but after the ring flip, this up methyl becomes, instead of equatorial, axial, and the up hydroxyl group after the ring flip becomes up and equatorial instead of up and axial, as it's shown here. Okay, so the reaction that's shown in the video is, even though it's called an aldol condensation reaction in the video, it's actually an aldol addition reaction, first of all. And then even more specifically than calling it an aldol reaction, we can call it a Hajost-Parrish-Eder-Sauer-Wiechert reaction, which I know is a mouthful, but there's credit being given to a lot of chemists here who developed this reaction from multiple different groups simultaneously. And essentially what that reaction is defined as in organic chemistry is a proline catalyzed asymmetric aldol reaction. And that's essentially what we're doing, right? We're doing a L-proline catalyzed asymmetric, meaning enantioselective, aldol reaction. And in the video, you're going to see that the preference is to form the R enantiomer over the S enantiomer. Let's look at a few other examples of this reaction, right? Because it's been used extensively in the organic chemistry literature as a tool in the synthesis of various steroids and other enantiomerically pure molecules. So we can see that in this case, they're using acetone, just like in the reaction highlighted in the video this week. But instead of using isobutyraldehyde, they use an benzaldehyde derivative with a para-nitro group. And it's still L-proline catalyzed. By the way, there's D and L, which are used commonly in biological molecules to represent stereochemistry, but L-proline is the S enantiomer of proline, which is the more common RNS designation that we're used to seeing for chiral molecules. Okay, so it's catalyzed by the same catalyst, and we end up with a good yield, 68%, and decent enantioselectivity, so 76% enantiomeric excess of the R enantiomer. Notice that the reaction tolerates a hydroxyl group at the alpha carbon and can react to form now an anti-selective diol product, which is a very interesting product to form from an aldol reaction. Notice the anti-selectivity for the two chiral centers remains the same even when there's not a hydroxyl group and instead an alkyl group, right, such as you would see with this aldehyde. Again, using isobutyraldehyde with the same catalyst, we're able to get 80% yield and actually fantastic 98% enantiomeric excess for this reaction, and an anti to syn ratio of 24:1, which is great. So notice the aldehyde, right? Here we have a benzaldehyde. The alpha carbon does not have any hydrogens here. Here we have a ring, right, a cyclohexane ring. There is an alpha hydrogen here, but there's only one, and this is a very bulky group, right, which is going to be very similar to isobutyraldehyde, which is used in the reaction in the video this week. Again, there is a hydrogen here, so you have the possibility of forming an enamine with isobutyraldehyde instead of with acetone, but the reason why that's unsuccessful is because of the bulkiness of the isopropyl group and the unlikelihood that this then acts as the nucleophile in the reaction. Let's look at the proposed catalytic cycle of the aldol reaction, which we can also know has that longer name, right, starting with Hajos. Of acetone and isobutyraldehyde with L-proline, they've abbreviated the isopropyl group as just being an R group in this case, because there are a variety of other R groups that can be used as well. So we can start the cycle here at the top between the catalyst, L-proline, and acetone, right? It can react to form an enamine. So these are the intermediates en route to the enamine. First, the nitrogen's lone pair acts as a nucleophile, doing a nucleophilic attack on the carbonyl carbon of acetone, right? Once we lose water here, we get an iminium ion, and a deprotonation at the alpha carbon will lead us to the enamine intermediate. The enamine intermediate will then have its carboxylic acid coordinate and hydrogen bond to the lone pair of the oxygen of the aldehyde, which is used as the electrophile in this reaction. When you show that hydrogen bonding going on, and there's even some thought that the nitrogen can get involved in hydrogen bond to the hydrogen of the carboxylic acid, you can start to see a six-membered-like transition state starting to develop here. And because this carboxyl group is pointing out of the plane of the page, it again holds the aldehyde in front of the enamine, right, instead of behind the enamine. Notice that the slide talks about a ray and a psi facial attack. That's referring to the attack with relative to this aldehyde, specifically where the R group is either on the left or the right, right? And so what we'll see here is that it is the ray attack, facial attack is preferred. Don't worry about the name and how it's derived. Just look at the fact that the R group is essentially going to be equatorial with respect to this six-membered ring-like transition state. From the psi facial attack, it's essentially in an axial position. So it makes much more sense to put it in an equatorial position because it will be more stable that way. So after the nucleophilic attack, where the enamine attacks the carbonyl carbons of the carbonyl of the aldehyde, we form this new carbon-carbon double bond. This is an iminium ion. With water present, the iminium ion can go back to the keto and the secondary amine. So it's essentially reversing the process of forming the iminium ion, right? With water, we can go back, so it's a reversible process. So water can do a nucleophilic attack on the carbon of the iminium ion, eventually leading to an alcohol group there. And then this can act as a leaving group. We can break this carbon-nitrogen bond, and will reform the carbonyl and the secondary amine catalyst. And the catalyst is free to react with another acetone and complete another catalytic cycle. The reaction this week highlights several principles of green chemistry, and that's why they call it a green enantioselective aldol reaction. The principles of green chemistry that the experiment illustrates are that the reaction proceeds at ambient temperature, which basically means room temperature, so you don't have to heat or cool the reaction, which is an energy input into the reaction. And it also occurs at ambient pressure, so there's no need to do to pressurize the reaction to get the reactants to work. It requires neither an inert atmosphere, which basically means that you can run it open to the air. You don't have to use a nitrogen gas atmosphere, nor purification and drying of the reagents. So they're able to do the polarimetry on the crude product. The word crude basically means that the product is used without purification beyond an extraction. So there is no column chromatography needed, recrystallization needed, distillation needed, etc., which are many different types of purification methods used in organic chemistry. So if they had to do those things, that would require more effort and reagents and solvents, which would make the reaction much less green. The reagents require no modification. Basically, you can just mix simple reagents together without first converting them to something else. And the promoter is used in catalytic rather than stoichiometric amount. So basically, you don't need a lot of the chiral catalyst, which is an advantage because catalysts are not incorporated into the product. So therefore, they're considered waste. And if we used a stoichiometric amount, meaning a molar equivalent, we would be producing a lot more waste. The catalyst is readily available in both enantiomeric form, so it's not expensive to get a hold of L-proline, and it's easy to get a hold of. You don't have to put a lot of work into synthesizing it. You can just purchase it. So those are all positives of the reaction. And the water solubility of the catalyst allows for its easy removal from the reaction mixture. So the fact that L-proline is soluble in water because it can form a zwitterionic form, which means it has a negative and a positive charge in its structure. We can easily wash it away from the reactants, and we don't have to do any further purification, which is fantastic. And both of the reactants are volatile. Acetone and isobutyraldehyde both have a low boiling point, so they're easily removed, which again means that we don't have to do any extensive purification to get the pure product. There are some trade-offs, though, for the reaction. In order to get the reaction in good yield and with good percent EE, acetone must be used in large excess, which destroys the atom economy, right? So if you're wasting a lot of acetone, technically, that means that your atom economy calculation is lower. The reason why acetone is used in large excess is because it functions as both the reagent and the solvent. And it helps suppress side reactions such as self-condensation of the isobutyraldehyde. So I mentioned before, it's technically possible for isobutyraldehyde to be converted into an enamine and then react with another molecule of isobutyraldehyde. And having a large excess of acetone will prevent that from happening because the likelihood that the enamine reacts with isobutyraldehyde, or sorry, the L-proline reacts with isobutyraldehyde to form an enamine is lower compared to the likelihood that the L-proline reacts with acetone. The reaction proceeds slowly, so this is a trade-off as well. The product does not even begin to appear until about 24 hours, and at least 48 hours is necessary to obtain an appreciable yield. I think in the video they let the reaction go for an entire week, so that's a lot of time that you have to wait for a reaction, which is a negative. Okay, let's discuss a little bit more. Why doesn't L-proline form an enamine with isobutyraldehyde? So the premise of this reaction is that you're using the L-proline and it forms an enamine with acetone. But why does it form an enamine with acetone? Why doesn't it form an enamine with isobutyraldehyde? Both acetone and isobutyraldehyde contain an alpha hydrogen, which is necessary to form an enamine. So it's technically possible for enamine to form with either acetone or isobutyraldehyde. We just talked about one reason, and there's a large excess of acetone being used, so that's really helpful to outcompete with compared to the isobutyraldehyde. It could form, right, as we talked about with the isobutyraldehyde, but the fact that once you form an enamine with the isobutyraldehyde, the enamine is much more sterically hindered than an enamine with acetone. Because of the two methyl groups, right, the nucleophilic carbon after the enamine is formed is going to be much more sterically hindered than if you were to form an enamine with acetone, which means it's unlikely to lead to a favorable reaction with another isobutyraldehyde or even acetone. Instead, it'll probably reverse course and eventually the catalyst will react with the acetone instead of the isobutyraldehyde. All right, at the end of the reaction, we want to check the enantioselectivity. We do this by doing some polarimetry and by measuring the optical activity of the product. The literature will tell us that the R enantiomer of our product rotates plane polarized light in the dextrorotatory direction, positive 66 degrees. The enantiomer, the S enantiomer, will rotate light in the levorotatory direction with the negative sign here, in the exact opposite magnitude as the R enantiomer, so negative 66 degrees. So what we need to do then is calculate the optical activity of the product that's formed in our reaction and compare it to the pure enantiomer, which we know the value of the optical activity from the literature. So this is the equation for calculating the specific rotation, right? This symbol in brackets. And what we do is we take the observed rotation, which is the observed angle of light that's rotated, divide it by the concentration and the path length. And you'll see in the video, he has a very modern instrument which is able to calculate specific rotation directly, given an input of concentration and path length. So essentially the computer does the calculation as opposed to the scientist. But also, in order to obtain a value that's accurate, we need to perform the polarimetry at room temperature. And specifically, I think they say 20 degrees Celsius, and the specific wavelength, which is usually the sodium D line. Okay, so once the sample is prepared with known concentration, it's put into a usually some piece of glassware of a fixed length, right, so that they can measure. At room temperature and a specific wavelength of light is used, the specific rotation is then calculated. It is then put into this equation to calculate percent EE. The observed specific rotation, absolute value, is then divided by the absolute value of the specific rotation of the pure enantiomer, which would be, again, 66 degrees. After you multiply by 100, you end up with your percent EE. Remember that this stands for percent enantiomeric excess. That means the percent of one enantiomer in excess, right, of the other. So when we are calculating the percent R and the percent S in the mixture using the percent EE, what we need to do is essentially start with the percent EE. For example, let's say that the chemist got an enantiomeric excess of the R enantiomer to be about 60%. Now, how would they know even that the excess is the R enantiomer and not the S enantiomer? Remember that to the literature known specific rotation for the pure enantiomers. So because the sample was rotating light in the positive direction, and they know that the pure R enantiomer rotates light in the positive direction, it is then concluded that the enantiomer that is in excess is the R enantiomer. Okay, let's assume that they got 60% EE. What that means is that if you take 100 minus 60%, right, the other percentage is split 50-50 between the S and R, and that this part of the solution is a racemic mixture. So because it's 60%, 100 minus 60% is 40%. If you divide that in half, because it's 50-50, that means that the part that's not in excess is 20% S and 20% R. So those are essentially canceling each other out. All right, this is the racemic mixture portion of the solution. And then there's the excess, right, of the R enantiomer. 60% is in excess, right, of the other portion, which is a racemic mixture. So then that means that there's 80% R enantiomer in the solution and 20% S enantiomer in the solution, right? So if you had 80% R and 20% S, that leads to 60% EE, because 20% of this cancels out the S, and then there's 60% excess of the R enantiomer. So the calculation is, right, take 100, subtract the percent EE, take the value that you get, split it 50-50, give 50% to the S enantiomer, 50% of that to the R enantiomer. Whichever one is in excess, add that to the 50% to get the total amount of that enantiomer that's in excess in solution, and then the remaining minor enantiomer. Okay, hopefully that was a good introduction to the video, and I will see you guys this week for office hours.